Hi, everybody. I'm John Keller, Chief Editor of Military and Aerospace Electronics Magazine. We're talking today with Bob Sgandurra, Director of Product Management at Pentek Inc. in Upper Saddle River, New Jersey. Pentek is an expert at blending high-performance embedded computing with RF and microwave signal processing for military applications like signals intelligence, electronic intelligence, and electronic warfare. We're discussing new generations of radio frequency system-on-chip technology, otherwise known as RFSoC, and what it means for applications like SIGINT, ELINT, and EW. Bob, tell us what RFSoC technology brings to the table for these applications, how it changes things from before these kinds of devices were available, where you see this technology going, and how RFSoC technology will drive the evolution of military and aerospace RF signal processing applications.
It's a lot of questions, but that's good. We have done this kind of technology with discrete components for a long time: ADs, D2As, FPGAs, separate processors. And I guess about 2 years ago, or actually 3 now, when Xilinx announced RFSoC, we saw immediate excitement because there was so much integration in that part. And it brought with it not only smaller packaging, but it also brought lower latency as a handful of different technologies in that part that really address things that were being done currently with a lot of discrete components, but the RFSoC provides a really unique solution. Just as an example, the A to Ds and D to As in that frequency range that we were using prior to this were typically serially connected with JESD. And while that's a good interface for a lot of applications, things like low latency, electronic countermeasures and EW cannot tolerate that latency between the A to Ds and the processing and the D to As. So having that all on one chip in the RFSoC lowers that latency and gives you a really solid solution for doing those kind of applications. That's just one of a few different places we've seen it.
Okay, it's been almost 4 years since Xilinx announced the RFSoC. Has it delivered as promised or expected, or have there been any surprises? What's the picture there?
Xilinx has done a great job. When Xilinx first announced this, again, the fact they were putting these RF class converters inside the FPGA, while again it was exciting, there was concern that the quality of those A to Ds, D to As, and those signals wouldn't be as good as, let's say, discrete components. But Xilinx delivered. I mean, the performance we're getting on the RFSoCs, the actual data converters in the part, are equivalent, and in some cases even better than discrete solutions from other vendors. So we're very happy with that delivery. Surprises, not a lot. Again, we've had good, solid support and performance from Xilinx on these parts. So overall, it's been a very, except for new technology things that always happen, it's been a very smooth development for us as a vendor and for our customers. There's some complexity in RFSoC that you don't necessarily see in discrete systems, because the ARM processor and the A to Ds and the FPGA and the DSPs are all in one part. I think to the uninitiated, there's a little bit of a learning curve. But other than that, we've seen, like I said, a smooth transition. And Xilinx did a very good job with the tools. So right in their tool package, either Bravado or now Vitis, they have support for all different technologies. So we're seeing it, a very smooth transition into this.
Okay, well, can you kind of paint a picture for me? I'm curious about what were the capabilities of high-end RF signal processing, 4+ years ago, before the RF SoC came on the scene, and how is it now, and what are the real, not so much the technologies, but the capabilities that the RF SoC will bring to the table for the actual EW SIGINT users out there?
I think, again, the low latency is a big part of it, especially for the EW users. We've needed that, and we've done that with parallel connections, but there was a limitation in terms of how fast you can go on the typical A to D, D to A. You got into the 1 gigahertz range, 2 gigahertz range. That's when things started to go serial. To be fair, a number of the vendors have come up with parallel interfaced A to Ds, D to As. But again, you're talking bigger packaging, and you're talking about a product that really can't be fit in a small form factor. So that's the other thing that's really very interesting about RFSoC. The density of the part and the amount of functionality in it is so much better than what you can do with discretes. And we took that to the next level. So rather than build a traditional board level product, 3U-VPX or PCIe, we developed a system on module, much smaller. And that system on module can go on standard form factors, but a lot of our customers are designing their own carriers because they can take a small board now with 8 channels of A to D and D to A, and they could place them behind antenna arrays, as an example. So where they might have had a few chassis full of equipment, they're putting the stones, with system on modules, right on their own custom carrier, sitting right behind, patch antennas. So that really didn't exist in that density a few years ago, and that we're really seeing a lot of people exploit now for things like phased arrays and high channel count systems.
Okay, so you said standard form factors? I mean, can this be used on 3U VPX, for example? I mean, what are some of the options that systems integrators have now with the RFSoC using standard open systems architectures?
Yeah, they're there. I mean, we have them, and our competitors have them too. We support 3U VPX. We have a SOSA aligned 3U VPX, PCIe. Because it's not only military, we've seen a wide range of different applications for RFSoC now. Traditional ones, SIGINT and radar, but others that are, like quantum computing. So the PCIe version of the board is very popular for those kind of applications because they're desktop systems. But anywhere you can put the SOM, you can pretty much put a standard form factor board. So it gives you a lot of flexibility, for developing systems.
Right. So in you're dealing with customers and potential customers, are you seeing more interest in an open system standard form factor type of approach, or what I think I'm hearing from what you said before is that there's a lot of custom design out there, particularly for some of the higher end applications. What's the picture there?
Yeah, I would break it down this way. I think about 30% of our customers are either going to use the small form factor or are designing a prototype, which is what most do in, let's say, 3U VPX. They're demoing it, they're getting all their software and their IP done, and with the plan to move to a custom form factor later on. So, like I said, about 30%, and we know this because we have a design kit that customers purchase it gives you all the design information on how to create the carrier. So we have a pretty good number in terms of knowing how many are using it. And about 30% are going towards a custom form factor. The other 60, 70% are still using primarily 3U VPX, and now SOSA aligned 3U VPX is becoming very popular.
And would you expect that 30% custom design approach to remain steady there, or do you see that diminishing over time as open systems architectures, become more popular?
Yeah, I think it's pretty consistent. I think what's going to happen is, again, it's the size of the form factor. So if for a man pack or something that you can't necessarily put even a single 3U VPX board in, you'll see that the SOM being used. But I think the percentage has probably been consistent for 2 years now since we started selling this. We had one of our first customers that we spoke to, we showed them a 3U VPX board with RFSoC, and they said, "That's great. Need something smaller." I mean, right out of the box. So at that
Wow.
point, we decided, let's offer all the standard form factors, but give customers an opportunity to go to something custom.
Okay. So, we've all been hearing for years and years and years that when it comes to RF signal processing, systems integrators need to be able to get the compute power, the data conversion closer and closer and closer to the sensor, i.e. the antenna for RF applications. To what degree does the latest generation of the Xilinx RFSoC enable them to do that? Are we getting closer to the sensor now? Are we getting closer to the ultimate goal?
I think we are. I think you're seeing again that these more densely packed chips, the small SOMs, are allowing you to get much closer. The other thing we do is the boards, and this is something that Xilinx has had for a long time, with the high gigabit serial interfaces. For instance, we have serial connections that we can provide as part of board design. So you see very often is the acquisition right up against the antenna, and even the pre-processing or the first level of processing and decimation. And then we use optical interfaces to move them. Let's say it's on a mast of a ship; they're going below, decks to do all the processing beyond that. So yeah, we're seeing that. We saw it with XMC. We've seen it with some of the other smaller form factors, but we're seeing it more now with this. Sorry, it was Pentek calling. Sorry about that.
That's all right. We've been talking about the Gen 3 RFSoC. What about the future, Gen 4, 5, 6, whenever those might happen? What would you expect from that type of technology? What would you see for the systems integrator, and for the user out in the field? What are some of the capabilities that we might see in the future?
Sure. It's always fun looking forward. And right now with Gen 3 already, we're seeing the higher bandwidth. So the Gen 1 part was a 4 gigasample per second part on the A/D. The Gen 3 that we're starting to ship now is a 5 gigasample. So already that difference, and also higher bandwidth on the front end, that difference alone is giving our customers more flexibility for, let's say, L-band acquisition. So much is done in L-band up to 2 gigahertz that the 5 gigasamples now on the Gen 3 part let you sample the entire L-band in the first Nyquist zone, which is really critical for a lot of applications. Xilinx has on their roadmap with Versal, which is their next generation of parts, an RFSoC. It's not an RFSoC, but it's an RF-enabled Versal part. And I think that's going to be the next big jump. With Versal, you have not only the DSPs and the fabric, but now you have the AI engines. The AI engines look a lot like GPUs or GPGPUs. So I think you're going to see not only higher sample rates, better resolution, but you're going to start seeing processing in there that customers right now are doing on multiple boards, like a GPU sitting next to a FPGA-based board. So I'm looking forward to that, because that again is going to bring us to another level of integration where in a single chip, you're going to get a lot of the processing and all the data conversion.
Right. Well, and trends in the military often are toward unmanned platforms, and I would anticipate that for electronic warfare, for SIGINT, for electronic eavesdropping, those types of things that really play into Pentek's wheelhouse. To what degree does the Gen 3 and future generations of the Xilinx RFSoC enable integration on smaller and smaller unmanned platforms?
Yeah, I think the Gen 3, again, because of the higher sample rates, we have interest in that right now. We have customers who are looking to get that already, and they've been developing with the Gen 1 with the intention of going to Gen 3 for the extra bandwidth. I think that, again, in terms of where we're going in the future, the density and the amount of processing that's going to be inside these FPGAs, especially with the AI engines, is going to give us some flexibility. I mean, a lot of what Xilinx is pushing towards right now is things like autonomous automobiles, where a lot of the radar and the imaging is being used for identification and for making decisions that are really analogous to what our military customers are doing. So that overlap, really, as Xilinx keeps moving forward with this technology, all our military customers, it may not be necessarily designed specifically for the military customers, but so much of that technology overlaps that we're looking forward to a lot of that coming up in the next few years.
Okay, back to the Gen 3 specifically, what are some of the applications that you see that will benefit most from the Gen 3 RFSoC?
I think the SIGINT applications in any place where you're going to be looking at, again, that little extra room you need to stay in L-band, it gives you that with the 5 gig. They went from 12 bits to 14 bits on the A/D. The extra dynamic range, we have it in-house, and we're just starting to really test it and qualify the performance, which looks good so far. I think that's going to give a little extra dynamic range to customers who are in things like SIGINT looking for small signals. So I think, probably, I'm guessing here, probably about a third of our customers, or maybe even a little more, have shown a lot of interest in Gen 3 right out of the box. They wanted that early on. They worked with Gen 1, and now they'll transition to Gen 3.
How difficult is it for systems integrators to move from the different generations? Is it a difficult design challenge? Does it require system redesign? I mean, what do you have to do to move from Gen 1 to Gen 2 to Gen 3 and to future versions?
I think the Gen 1 to Gen 3, it's the same tool set. It's a lot of the same IP. If you think about it for a minute, what Xilinx did is in the Gen 1 part, they had decimations and interpolations of 2, 4, and 8. It was pretty limited. In the Gen 3, they have 2, 3, 4, 5, a lot of really interesting numbers between 2 and 40. So when you start going in and you start decimating and you're changing your data widths or your bandwidths in general, just moving the data through, you are kind of changing the plumbing inside the FPGA. So as you'd expect when you're going from a Gen 1 to a Gen 3 part, if you're still using some of the same decimations and some of the same rates as the Gen 1, you're not going to see much difference. If you want to exploit some of the new features of Gen 3, then you're going to be porting your software and making changes to the IP. I can't speak for Versal yet because it's really not out there with RF, but I think the transition from Gen 1 to Gen 3, at least for current RFSoC, is pretty well defined. You just need to, again, if you're going to exploit those features, you really need to know there might be some changes to handle how all that plumbing works to get those different decimations or higher speeds.
Okay, you had alluded to it before when you talked about the learning curve of of moving to the RFSoC. Could you go into some detail about what are some of the biggest challenges to using the RFSoC?
Yeah, I think that our customer base is pretty well versed in, they're very well versed actually in FPGAs. And one of the things that we've always done is we've made sure that our tools are designed to give you the quickest path to development. So, for instance, all of the IP libraries are backed up with software libraries that are well integrated. So any IP module has a software control module, and that way, when you're developing, you can find you make changes to the IP. You can easily find where you need to, let's say, change the software to control the new IP. With RFSoC, if you haven't done system on chip before and you haven't used the ARM processors, it does add another level, which is Linux support. If you approach the RFSoC and even the MPSoCs, which are the other parts from Xilinx without the RF, if you approach them understanding that the ARM processor is such an integral part of the chip, it's not just an add-on processor. That's kind of where you have to go, and that's one of the challenges that customers who haven't used MPSoC sometimes tend to assume it's just another processor on there, but it's really an integral part of the overall operation of the chip. So what we found when we first started designing with it is that our software engineers and our IP engineers that always work together are working even more together now because they were, they were developing Linux kernels at the same time they were doing the IP and the application. So it's another level of once you understand the technology, it works really well. The tools support it, but there's a little learning curve, kind of just understanding how everything works together initially.
Okay. Well, I wonder, do you have any idea about the announced Xilinx acquisition of AMD and how that might change the technology landscape, particularly for systems integrators and users in the field?
I think the acquisition. I think we kind of knew at some point that Xilinx would either merge or be acquired. But if you look at what Xilinx revenues look like for the past few years, if you take any quarter, you'll see that anywhere from 35 to 45% of their revenues are, mill aerospace and measurement and test and measurement. And if you look at that slice, a big part of it is mill. So I don't think Xilinx is going to be moving away anytime soon from that market. A big chunk of where they're selling is into the military. Do I expect to see an AMD Xilinx banner ad that says, Versal RF is the best thing for phased array military systems? No, but the technology overlaps so much that I think it can only be a good thing if AMD and Xilinx continue to develop this technology. So I think we're going to see again a lot of that overlap. What Xilinx is doing in 5G, in big data, in supporting autonomous vehicles, a lot of that technology can be leveraged by the military, or our customer base. So I expect it to be a good thing, I think, long term.
And how do you see that potential acquisition influencing tighter and tighter levels of systems integration and putting more capability on a chip, particularly to systems integrators who are interested in very tight applications like unmanned vehicles, that type of thing?
I think Xilinx was on that path. If you look at what they were doing again with the AI engines, um, I think they were really moving in that direction for tighter integration. And they certainly were moving towards markets that require that integration for edge technology and for, again, things like autonomous vehicles, where you're in a small package with a lot of performance. Again, I think if AMD and Xilinx balance it right, I think the resources they can get from AMD and vice versa should work out very well. It really turns out, it depends on where, again, they're focusing on specific details, but I think overall the technology across both companies really does serve our kind of market very well.
Okay. Well, I would like to thank you, Bob Sgandurra, Director of Product Management at Pentek Inc. in Upper Saddle River, New Jersey, for being with us today and for a lot of those terrific insights. So thanks for tuning in, everybody. I'm John Keller, Chief Editor of Military and Aerospace Electronics.
Thank you, John.